Okay, shall we start? Okay, we're happy to have Yunfeng from Nanjing. He's going to talk about the integrability perspective on TTbar deformation.
Okay, thank you very much, and good afternoon, everyone. I would like to thank Satoshi and the organizers for giving me the opportunity to talk here. So my topic today is about TTbar deformation. And I checked the list of talks. These are among the only two talks that does not have supersymmetry. And but I hope it's still interesting to some of the audience. After all, our universe might not be supersymmetric. This talk is based on two papers which came last year. So the first one is in collaboration with my postdocs, Miao and Hou Jue, and second one is just by myself. So let me first give you some motivation or introduction, what kind of problems we are interested in. As some of you might know that starting from 2016, a subject called TTbar deformation has become a kind of hot subject. So now I want to briefly summarize why you might be interested in TTbar deformation. So it's defined in this way. Basically it's a family of theories, and it's an irrelevant deformation. So here this L is the Lagrangian density of your QFT. By the way, this is defined only for 1 plus 1 dimensions. Well, some people try to define for higher dimensions, but it's not as successful as in 2 dimensions. And this lambda is the deformation parameter, and then this TTbar is a very specific operator, which is basically the determinant of the stress energy tensor of the theory. So why this theory is interesting? So the first reason is that it's solvable, in the sense that if many deformed quantities can be computed analytically. So this is an irrelevant deformation, but most irrelevant deformations are quite complicated, and this one is rather simple. So that's why you can make some progress, and people are interested. And secondly, it gives rise to a kind of new QFT, in the sense that it's not the usual local QFT, but it has some non-local features like gravity field. So this gives something new. So if there's something which is simple and new, then of course many people will be interested in that. And after 7 or 8 years, there has been many papers on this subject, and they come from different communities. So here I just briefly summarized the different motivations to study TTbar deformation. The first community comes from integrability, and the reason is simple, because these original papers, these 6 guys, all of them are integrability experts. So they actually, the study of TTbar deformation, one of the origin is from integrability. And the reason that people are interested in the integrability community is that TTbar deformation preserves integrability. It means that if you start with an integrable QFT, then you do the TTbar deformation, it is still integrable. And it gives rise to a new kind of integrable model, so that's why it's interesting from people doing integrability. So a second, which I think is the biggest community who's interested in TTbar deformation, is from holography. And the reason is also simple. If you believe in ADS-CFT correspondence, and you know that you take the CFT, you can do TTbar deformation, then the very natural question is, what happens in the bulk? What is the bulk holographic dual of the TTbar deformed CFT? So this motivates people to study TTbar deformation in the holographic community, and we have gained many intuition and knowledge in this question. Yet another community which might not be familiar to most people is that come from the QCD string. Around 2010, there are people who try to revisit the effective string, which describes some low energy effective theory in quantum chromodynamics. And this is described by some effective long string, and they start to study some scattering on this long string. And in this way, they find the first example, actually, of the TTbar deformed theory, which is the TTbar deformed free boson. And there you have this Namukoto stream, and probably many people are familiar with that. And then, of course, there are other motivations, which something like the 2D gravity or SYK, that I don't know, and I don't have time to summarize that. So let's see, after 7 years, what have we learned? The first thing we learned is that that deformation, the definition of the deformation, which I just written down in the first slide, we now understand that TTbar deformation can be reformulated. And it has nice reformulation. It is equivalent, so turning on the TTbar deformation is equivalent as putting this theory on some random geometry, or couple this theory to some simple 2D JT-like gravity. So this is a nice formulation. And we made a lot of progress in computing observables, exactly. And these observables, they include the deformed Lagrangian at the classical level, and the S matrix, deformed S matrix, which is very simple. At the quantum level, also the deformed spectrum, the torus partition function, and some other quantities. And we also understand much better what is the holographic dual of the TTbar deformation from ADS-CFT correspondence. So for one sign of the deformation parameter is the cutoff geometry, and for the other sign is this glue-on geometry. So we shouldn't say glue-on because it's a different meaning. So, and then you have a different interpretation with this mixed boundary condition from Monica Guica. And then there's also a community of people who are studying a related deformation called a single trace TTbar deformation, and that's very interesting from the stream worldsheet point of view because it corresponds to some marginal deformation on the stream worldsheet. So to summarize, after 7 years efforts and with about 400 papers, we understand many things. But of course, like any field, so even for supersymmetric gauge theories, which have even much more papers, there are still open questions, and important ones. So there are many open questions. Here I'm going to be very biased. I'm just going to highlight 2 questions, which I think is interesting, at least for me, and I hope it's also interesting for some of the audience. So the first question is about the computation of correlation functions. So previously we have computed most of these objects are related to spectrum or on-shell quantities. So there has been very little progress, not so much progress in the computation of correlation functions. Here I want to emphasize what I want is this non-perturbative computation of correlation functions. Because you can always do CFT perturbation theory to first order or second order. But perturbation theory doesn't tell you much. Actually, the interesting thing in TTbar deformation is really the non-perturbative result in this deformation parameter. Because at the first few orders, you cannot really distinguish it's the TTbar deformation or some other deformation. And why this is interesting? Because correlation functions, I think, is probably the most interesting observables in quantum field theory, especially if you want to make comparison with experiments, like in condensed matter physics. So the things that you can measure and you can compare with experiments are essentially correlation functions. And these guys are actually, at the same time, they are very challenging to compute. Even for the undeformed theories, like you take, imagine you take some random theory, like QED or lambda phi 4, and you imagine you try to compute some correlation functions. This is much harder than computing the spectrum. So it's very hard to compute the correlation functions even in the undeformed theories. But in some cases, we do know correlation functions, like in 2D CFT. And so this is an important and challenging question. So I think it's how to understand these objects in TTbar deformed setup is interesting and worth starting. So last year, there has been some important progress in the non-productive computation of TTbar deformed CFT. So these are the 2 papers. So the first study of this kind is by Kadi in 2019. And the second question probably is a bit more blur, in the sense that we all know by studying TTbar deformation, we know that things will go wrong at certain energy scale. So you can look at the deformed spectrum or the partition function. There are explicit results. And you look at this result, you find that at certain energy scale, there will be singularities. And beyond that, we don't know what happens. So we all know that things will go wrong at a certain scale, but what we don't know is what actually goes wrong and how can we cure this? Physically, how do we think about that? For example, in QCD, if you compute the thermal partition function, you know that at certain temperature, you will hit some singularity. But in QCD, we know this singularity corresponds to a phase transition, corresponds to this Hagedorn transition. And here, what we know is that mathematically something goes wrong. But physically, what is the interpretation? How can we go beyond that? Is there a phase transition, or how do we think about that? So this is another important question that we need to understand.
So would this happen for supersymmetric theories?
Yes.
Also, like if I take Landau-Ginzburg model, could this actually happen?
I think yes.
So TTbar deformation would hit some similarity.
Yes.
But I thought it's a Q-exact deformation.
Hmm? No, this is an irrelevant deformation.
Yeah, but it's also Q-exact, right?
So for supersymmetric theories, you need to actually define what is the supersymmetric version of that TTbar deformed theories. And I think there has been some studies. I'm not sure if Landau-Ginzburg or other, but it's find the same kind of. If you compute the partition function, it's the same kind of singularity. It will occur. So this is a generic feature. Yeah. Okay. So
the typical energy scale? It's governed by what?
So for two different signs, there are two. For two different signs, there are two kinds of singularities. For the negative sign, you will have singularities in the low energy spectrum, and this size is proportional to the central charge, and also it depends on. So you need to put your theory on the cylinder, the finite length, and depends on that length. So on the other side, for the other sign, you will see some singularities when you compute a partition function. So for that, you will have a kind of Hagedorn singularity, and that one is also determined by the size of the system you start with, and also this TTbar deformation parameter because it's dimensional. So yeah. Okay, so these are two challenging and important questions, and I don't claim that we can, or I have a full solution to these questions. So in this talk, my goal is rather modest. So I'm an integrability guy. I try to go back to integrability and look up the toolbox. So there are many tools in integrable models, and some of this toolbox hasn't been fully explored in the TTbar deformed context. So I want to go back to integrability and see that are there any tools that I can make use to solve this kind of problem, or at least make some progress, some partial progress, towards the understanding of these two questions. So that's the main part of my talk. So the first part is about correlation functions. So in integrable models, there's a standard approach called form factor bootstrap approach, which computes non-perturbatively correlation functions in massive integrable quantum field theories. So the natural question is, can we generalize this method to the TTbar deformed theories? That's question one. So for the second one, which is what happens in the UV. So we know there's a nice way to handle UV divergence, which is putting a QFT on the lattice. So I will discuss this in more detail. And then in integrability, for some theories, there's a way that you can put the theory on the lattice in an integrable way, so that you obtain some integrable lattice model. So then the question becomes, what is the corresponding lattice deformation that in the continuum limit becomes the TTbar deformation? So these are the two questions I want to make some progress. And so then I will go to these two parts. So in part two, I'm going to introduce you what is the form factor bootstrap. Let us start with a big question about solving the QFT. What do we mean by solving a quantum field theory? So I think in the most strict sense, it means that we have the ability to compute all on-shell quantities, like S-metrics, and all off-shell quantities, like correlation functions, non-perturbatively. Of course, this is just a dream, right? We know that it's extremely hard for generic QFT. But in some cases, we can do a bit more. In some theories with more structures, like if you have supersymmetry, if you have sufficiently many supersymmetry, then you can ask for more. You can imagine that you can compute something non-productively, like indices and like the spectrum and some correlation functions. So supersymmetry is one kind of theory which we can ask for more for solving the QFT. And another important class of QFT, which you can hope to solve, is integrable quantum field theories. And the non-productive method we are going to use is called bootstrap. So nowadays, bootstrap has been used a lot, but this is really one of the first contests where people use the word bootstrap. So the idea is that actually there are two steps in solving integrable quantum field theories. In the first step, we try to fix the S matrix. The reason is that in the integrable quantum field theory, all the scatterings, m-particle scatterings, will be factorized to 2-to-2 scatterings. So the 2-to-2 scattering S matrix will basically contain all the dynamics of the field. And how do we fix this S matrix? Instead of starting from the Lagrangian, we impose some general consistency relations, including unitarity, crossing symmetry, and importantly, Yang-Buxton equation. So this is special for integrable QFT. And we also make analyticity assumptions about this S matrix. And with some perturbative inputs, which we can specify the S matrix, because all the S matrices have to satisfy these conditions. So how do you distinguish different theories? So in this way, you still need some perturbative input, but that's not too much. So, and this has been quite successful in integrable quantum field theory. Now we know the S matrix non-perturbatively of many IQFTs, like Sine-Gordon, Sinch-Gordon, Ising, scaling-Young, and affine Toda, many things.
So
Now,
initially you mentioned 2 dimension.
2 dimensions, yeah. So we cannot do much in higher dimensions. And now, after you fix this S matrix, then the next step you want to compute are correlation functions. Then you take this as an input, and you go to the second step. In the second step, so we want to bootstrap the form factors. In a similar philosophy, instead of computing Feynman diagrams, we impose a set of axioms, and then we solve these axioms to find the form factors. So essentially, form factors are just matrix elements of local operators, and so I will describe in more detail how to solve them. Now, suppose you want to compute this 2-point function. What you can do is you insert a resolution of identity here, right? And then each part, this matrix element, is what I call the form factor. So if you can compute this guy non-perturbatively, and then compute this guy non-perturbatively, then you can try to take this sum, and then compute this 2-point function. So that's the philosophy. It's very simple. Now, in integrable QFT, this can be made more precise. So this resolution of identity takes this form. We can first sum over this m-particle sector. So you have 0 particle, 1 particle, 2 particles. So this is what the summation over m means. And then within each sector, we integrate over the rapidity of the particles. And these are the rapidities which parameterize the energy and the momentum of your state. So this m cos theta k is the energy of each particle, and m sinh theta k is the momentum of each particle, and this satisfies the 2D kinematics dispersion relation. Okay, so our goal is to compute this guy, okay, the form factor. And how are we going to do that? So this on the left-hand side is the input. Okay, so sorry for people who don't read Chinese. So in the left-hand side, what do we have? We have the input of this S matrix, which contains the dynamics of the theory. We have the input of this operator, which contains information of your operator. So this includes like vacuum expectation value, conformal dimension of these operators. And then we also need to make analyticity. So these are the inputs. And you put it in this machinery, and then which I will describe in detail. This machinery is basically a set of axioms that you need to solve, and after that you obtain this guy. And I want to emphasize that this is axiomatic. There's no pollution from Feynman diagrams. It's non-productive. Yeah. Okay. So what are these axioms? It's very useful to have a diagrammatic representation for the form factors. So this circle represents some operator, and these arrowed lines correspond to some incoming particles. And this guy will describe a form factor. The first axiom is called the Watson's equation. So remember, in 1 plus 1 dimension, these particles are ordered. So you order from left to right, theta 1 to theta n. So this axiom tells you that if you swap the order of two particles, like theta I and theta I plus 1, then you need to pay for an S matrix. So the S matrix, as I said, is an input, so it comes in here. So in terms of equations, so here you have theta I plus 1, and here you have theta I plus 1, theta I. You swap the order, you multiply with the S matrix. So that's axiom 1. And the axiom 2 is that you can take this the first particle and put it to the last one, but you need to shift it by 2 pi I. And then the claim is that these two form factors should be the same. So this is called cyclicity commutation. And what's more interesting is this kinematical singularity. So this means the following. Suppose in your form factor, there are two rapidities whose difference is I pi. So this means you have this kind of configuration. And if you have this situation, then this guy can just be factorized out. It can be factorized out either directly or go through all these particles and then factorize out. So this is reflected in the analytic property of your form factor. It means that at this point, there will be a pole. There will be a simple pole. And the residue of the simple pole is given by the form factor with two less rapidities. So finally, we have this dynamical singularity. So this applies for the theories where you have bound states. So suppose you have two particles with the rapidities, that is exactly enough to produce a bound state. So then this will also be reflected in the singularity of your form factor. And this is related because the bound state is also given in this S matrix. So you at a certain point in the complex plane, you will have a pole in the S matrix, and you also have this pole in the form factor. So these are the axioms that you need to solve. And we need to make some analyticity assumption. So we assume that the form factors are meromorphic functions of the rapidities. And since they are meromorphic functions, they have singularities. Now the requirement is that all the singularities must have physical origin. They either come from kinematical singularity or come from dynamical singularity. You cannot just come and put a random singularity in the form factor. So that's the maximum analyticity assumption. So these axioms, you might wonder, where does come from? So in some cases, you can derive it from the LSZ reduction, from some very general assumptions in QFT, and this is not easy. But anyway, this method seems to be very successful in the past 3-4 decades. So I emphasize that all the operators, the form factor of any operator should satisfy all these 4 axioms. Then the natural question is, how do you distinguish then different operators? So the point is that when you solve these axioms, you need extra input, some extra information, like the expectation value, and also this asymptotic behavior, and also after you compute these form factors, you need to check with other methods to be consistent. And this all has been done in the usual IQFT.
So which one of them, these axioms, which one of them depend on the theory should be to?
Oh, I think a lot of them. So first there was an equation, because this is a 2-particle S matrix, and probably this well, kinematical poles I think is true for any theory, and Yeah, this should also be true for arbitrary theory. So indeed, some of these axioms are true for generic QFT, but some of them are only true for integrable QFTs. So there are also, I remember there's also a program, because there's a program currently, people are revisiting the S-matrix bootstrap, mainly from the numerical point of view. And there's also a generalization like this to revisit the form factor bootstrap, and there you can find a list of axioms that they assume which should be valid for generic QFT.
But presumably these are for local QFTs, right?
Yes.
But then you mentioned in the beginning that TTbar is
Good point,
slightly
yeah.
non-local. First of all, I would not understand what that means, given that T and TTbar are local operators.
Yes.
But somehow.
That's a very fair point, and I hope I have time. If I have time, I will explain in more detail. So let's just give you probably one answer is that in a local QFT, we know that the S matrix should be bounded. So there's this Froissart bound which should be applied to any QFT, which means that if you extend your momentum to infinity or understand variable to infinity, it should not grow faster polynomial. But in TTbar deform theory, this is violated. So it grows faster, it grows exponentially. So in some classifications, it's called a quasi-local quantity theories. So this is one of the reasons. And also you have all kinds of singularities like the Hagedorn behavior. If you compute the torus partition function, and then you can use the Cardy's trick to look at the asymptotic growth of the density of states. And you know for a local QFT, it has Cardy behavior. So rho grows like exponential square root of E. But in TTbar deform theories, if your deformation parameter is large enough, it grows like exponential E, which is a Hagedorn behavior. That is more typical for string theory and gravity theories. So for these kind of things, we say this is a non-local theory.
Okay, so you are saying that Cardy's formula also in general work for non-conformal theories? And
because Cardy's formula requires modular invariance. And we can prove that modular invariance is preserved in the TTbar deform theory. Okay. So how do we solve these axioms? It looks very difficult. It's a set of functional equations. So the smart people solve this for us, like Smirnov. And the usual strategy is that you make an ansatz. You make an ansatz like this. So here you have a product of terms. And this is called the minimum form factors. So there's a theorem which you can compute this minimum form factor is determined by the S matrix of the theory. And this is the universal part. So any form factors, and this encodes this Watson's equation. So S matrix appears here. And then this part in the denominator encodes the kinematical singularities. And then the operator dependent part is here. So here is Q is a polynomial in terms of an exponential theta. And to find this guy, you actually need to solve the singularity axioms, including the kinematical singularity and the dynamical singularity. You need to solve them recursively, and it's precisely in this solution you need some initial condition. You need some extra inputs, and this is where the information of local operator enters. Okay, now TTbar deformation. So we start to do TTbar deformation, then we ask ourselves, what is changed? So we have two steps, right? The first step is bootstrap S matrix. The second step is bootstrap form factor. And for S matrix, it has been done. We know that it's changed in a simple way. It's simple, but it's weird. Because suppose this S matrix is polynomially bounded, and then if you look at this large theta behavior, you see this grows, this oscillates extremely fast. So it's not bounded. So this guy is not bounded polynomially. And now we want to make progress with form factor. By the way, this is called a CDD factor. CDD refers to three physicists, Castellejo, Dalitz, and Dyson, who studied this kind of functions in the 60s. And because these functions, they automatically satisfy unitarity, crossing, and so if you take S matrix, multiply any CDD factor, it's still unitary and satisfies crossing. So that's why it's called a CDD factor. So now we want to understand how does the form factor change. So we make some assumptions. We assume that the same bootstrap axioms, the 4 axioms, which I just listed before, we assume that it's still valid for TTbar deformed theories. But this is a reasonable assumption, but we don't have a proof that it's true. So why do we believe in this? Because other integrability methods, like thermodynamic beta ansatz, like asymptotic beta ansatz, they can all be applied to the TTbar deformed theories and they get the correct results. So I believe integrability seems to be a very rigid structure that you can make use of. So that's our faith why we can use this. We can still apply these axioms. But of course, it would be nice if we can prove or justify further that these axioms stay the same. Now, suppose you assume that it's the same, then you just turn on your machinery, you change your input, and see what does the output changes. And one thing is that the solution of the form factor bootstrap axioms is not unique, and we need to fix ambiguity. So people made partial progress in this step. So what has been realized last year, actually this is a very recent result. I tried to play this game 3 years ago, but without success. But it was scooped last year by another group, which they made a very smart factorized ansatz. Well, it's not that smart, it's the simplest ansatz. But I was not smart enough to make that. And then you find that it takes a factorized form. So this is a minimum form factor. Remember, it's one part of the form factors. There's a minimum form factor, and they propose that it's actually the undeformed guy multiplies some other factors. And this phi is the part depends on lambda, which is the deformation parameter. And then you have this ambiguity part, which is a form factor version of CDD factor. So this part you cannot fix. Basically, you take any of this function belongs to this family, you multiply this, it satisfies these axioms, form factor axioms. Okay, and then for this part, which is the polynomial part, you can also make this factorized ansatz, and you find that you can indeed find a solution to the deformed axioms, to the axioms that with deformed S matrices. But I want to emphasize that, so this seems to solve the problem. So you make a factorized ansatz, and indeed you can fix the deformed minimum part and the deformed polynomial part, and you can fix them up to some ambiguities. But I want to emphasize that so far, this ansatz is only worked out for a very simple model. This is the model with only one type of particle with diagonal scattering and no bound state. Essentially, these are just the easy model, or the Sinch-Gordon. So for more complicated theories, including bound states and more type of particles, we still need a lot of work. And it's not clear this factorized ansatz will work automatically, or maybe some modifications are needed. Okay, so this is the story for the deformed local operator, but I still want to comment on the fact that actually you can compute also the entanglement entropy, entanglement measures using the form factor bootstrap approach. So what was the logic? So this is the entanglement entropy, which people usually define. You take a partial chase in your system, and this gives you the reduced density matrix, and then this is the von Neumann entropy. So the standard way to compute is by replica trick. So you make many replicas like this, and then you do the chase of this replica, this row A to the power of n. So one thing you realize is that this chase can be computed as a partition function on some Riemann surface. And the key point is that this Riemann surface, the partition function on this Riemann surface, can be computed as a two-point function of a special operator called the branch point twist field. And this is a two-point function. So you can do spectral decomposition and so on to try to find the form factor of this branch point twist field. So we need to find this guy. And here you have some additional indices which labels which sheet you are on. And then, and indeed you can find the form factors for the branch point twist field, and this has been done back in 2007. And we can also do the TTbar deformation in this case. But now you have a replica theory. So you need to be careful that after TTbar deformation, if you are on the same sheet, then you pick up this CDD factor. If you are on a different sheet, then it's different. Then you don't scatter. So with this modification, we can also find out the deformed form factor for the branch point twist views, and then we can compute this deformed entanglement entropy. And we find that for lambda smaller than 0, which is one sign of this deformation parameter, the change is very simple. You change the central charge. And for the other sign, the integral is divergent, and we don't know how to handle this. Because here in this computation, we only take remember we have this CDD ambiguity. We only take into account the simplest CDD ambiguity, and then this is the result we get. So the bottom line is that the information I want to convey here is that we can do something. We can solve part of these axioms, but there are ambiguities which so far we are not able to fix. So the point is that we can find solutions, some solutions to the form factor axioms, but we are not completely sure these are the correct solutions. So there's still a lot to be done in this area. So this is just the starting of this business.
So which theory this entropy?
Ising.
Ising.
We are computing Ising, yeah. Because
So
in
mass-
this theory, everything we know.
What is the M?
M is the mass. It's off critical Ising. It's a massive free fermion. Okay, now I go to the
So
second part.
Negative lambda is the cutoff side or glue. Which one?
Let me see. It's most likely the part. Let me see. I don't remember clearly, but let me not to make some stupid.
Because you said for the other side the is divergent, so we
Yeah, it's divergent because you have this because you multiply some factors like this, and then it's easy to see that when you do the integral, it's divergent or it's convergent. But the sign is different.
and naively probably the second one is the glue one because you asked the small.
That's possible.
Okay.
Yes. But but still we need to understand this. It's just divergent, we don't know. Maybe there's some cure to this divergence. Okay, so now let me go to the second part, which is about lattice regularization. So before going into details, let me comment on this relation between QFT and the lattice models. So there's a perspective on quantum field theory, which is, I think, is dominating in the condensed matter community, is that QFT actually describes some low energy, long wavelength physics of some underlying models. For example, if you have a 2D Ising model or any dimensional lattice Ising model, and then you tune your temperature to the critical point, then in the continuum limit is described by the Ising field theory. So this is the prototype of this kind of thinking. So there's some there's some underlying model in the UV, and then if you take the continuum limit or you investigate some low energy, long wavelength limit, you will find the QFT description. So this is the more condensed matter point of view about QFT. Or we can also make a connection of QFT and lattice model by putting a QFT on the lattice. So this is what people in the lattice QCD are doing. And originally, this is a way to regularize the UV divergence, right? Because if you do perturbation theory, you have UV divergence. And then if you regularize that, then in the UV, you just approach the lattice. And then you can put your lattice to do numerical simulations. So that's another way. So lattice QCD is another non-productive way to really solve a strongly coupled quantum field theories. So why I want to investigate this point of view? Because as we know, TTbar deformation is an irrelevant deformation. So what does it mean? It's irrelevant in the IR sense, in the sense that it doesn't change the long distance physics. But if you zoom in, if you go to the UV, you will see a big difference. That's what we expect, right? And then if you take this lattice point of view, namely if you go to the deep UV, you should start to see the structure of the lattice model, the underlying lattice model. And I want to understand what do I need to do at the lattice level in order to obtain the TTbar deform theory in the continuum limit. So that's the rough idea. And so for integrable QFT, we can do a bit better, because after you discretize this theory on some lattice, there's no guarantee you can solve this model. The lattice model may be even harder than the QFT, and then you are a bit stuck. Otherwise, you have to just to do numerics. So in the integrable QFT, you can actually do this discretization in an integrable way for some theories. So here I present, okay, so this is the philosophy I want to present. Suppose I have a QFT, and I know its lattice model. And suppose I do a TTbar deformation to this QFT, and then the question is, what do I need to do on the lattice?
But in general, from infinite to UV is far from unique.
Yes, it's not unique. Yeah, so I'm just going to investigate one of them. But I believe there should be some universal feature which should hold for all the discretization. Because TTbar is a rather universal deformation. But I agree, yes, there's a non-unique way to discretize your theory. So here I'm just
there may not be a single way, right?
What?
There might not be a single way.
Yeah. So there might not be a single way. So you can take different lattice and then they will flow to the same.
I mean, it could be that there are no lattice that flow to the theory, right?
It's also possible. So I'm just assuming, so suppose in the case where I know there is, then what do I do? Yeah. Yes, it's not guaranteed every QFT has a lattice dual. For example, for some non-Lagrangian theories, I don't know. You don't even have a Lagrangian, what is the lattice? I don't know. But anyway.
I think these are probably fine, but usually CFT would have lattice duals. But other QFTs, you worry that from the lattice to the infrared, Lorentz symmetry may not be restored, right? But probably we will see later in your example whether Lorentz symmetry is present or not.
In that case, I think Lorentz invariance wouldn't play an important role. You'll see in my way of taking the continuum limit. So what plays an important role that unifies the lattice model and the field theory would be integrability structure. Yeah, so there are different ways to take the continuum limit. And also, even for the same lattice model, suppose you are on a different vacuum, you take the continuum limit in a different way, you will reach at a different field theory. So indeed, this is not unique. The procedure is not unique. So I'm going to tell you some very concrete example. So the field theory I want to investigate is the sine-Gordon theory. This is a prototype of integrable quantum field theory. And the lattice model I will going to describe is the following. So we consider this light cone lattice of this shape. And at each point, or each vertex, I have 6 possible configurations. So you always have 2 incoming arrows and 2 outgoing arrows. So this will give you 6 possible configurations. And this is called a 6-vertex model. And this is a light cone 6-vertex model. And for each configuration, I associate it with a Boltzmann weight. Here, A, B, and C. And here at each line, on each line, I associate it with a parameter called the spectral parameter. These are U and V. So the Boltzmann weights will depend on the spectral parameter that you put. And so how do we see that this model is integrable? You can actually organize this Boltzmann weight into this matrix. And you'll find that this matrix satisfies the Yang-Buxley equation. So this is the Yang-Buxley integrability of this statistical mechanics model. Now, so these are the explicit expressions for A, B, and C. So this is also the R matrix of the XXS spin chain. So here kappa is some parameter. Now for lattice model, the basic task you need to do is to compute its partition function. So suppose I give you a lattice model, I tell you the possible configurations, then you just sum over the configuration and find the partition function. And after that, you can find the thermal quantities from the partition function. So the basic task is to find the partition function. And this can be done by the so-called transfer matrix method. So the idea is that you multiply this along this dashed line, you multiply its R matrix. So after you multiply this row and this row, and so this will give you the so-called diagonal to diagonal transfer matrix. So it's an operator, it's a transfer matrix, and once you obtain this transfer matrix, you just take it to the nth power and take the trace. So this gives you the partition function of the lattice model. So after defining this transfer matrix, so by the way, transfer matrix is also one of the standard methods to compute partition functions of the lattice model. And then you can define the lattice Hamiltonian, because this transfer matrix, you can view it as a kind of discrete time evolution. So you can define this Hamiltonian formally this way, and here A is the lattice space. So, okay, even I reformulate it in this U, then how can I make progress? How can I just compute this object? So the key point is that for an integrable lattice model, we can diagonalize U by integrability methods. And indeed, the transfer matrix can be diagonalized by beta ansatz. So you can have a systematic way to construct the eigenstate of this operator U. And so this is the n marginal beta state which you can construct. Here, this theta is here. So I told you that the Boltzmann weight depends on the spectral parameter. So here I choose it in a funny way. So this is theta, this is minus theta, this is theta, this is minus theta. I choose it in an alternating way, and this theta will play an important role later. So anyway, you can diagonalize U, and you can find its eigenvalue explicitly in terms of the so-called beta roots. So this Uj are beta roots, which you need to introduce if you apply beta ansatz method. And these beta roots need to satisfy a set of equations called beta ansatz equations, which looks looks a bit complicated. So if you are on the lattice, say a finite size lattice, then what you need to do is you need to solve this equation. Typically, you solve it numerically. You solve them, you find solutions of beta ansatz equations, and then you can plug in this solution to this expression. And then you take nth power, this gives you the partition function, and we are done. Now, our goal is to take the continuum limit and make connection with field theory. So in the continuum limit, different solutions of these beta ansatz equations, they will correspond to different states in the field theory. And one particular state is the vacuum state, or the ground state of the Sine-Golden theory, and that would correspond to a special solution of this equation. And this special solution is called the antiferromagnetic vacuum state.
Does this equation have correspondence in supersymmetric case theory?
Which supersymmetry?
No.
If you take this theta, I think the answer is yes. Because this is essentially the beta ansatz equation of inhomogeneous XXZ spin chain. And as I learned from Marcus, it corresponds to sub-theories who left us, unfortunately. But yes, I remember there is this kind of in the beta gauge duality. So we're looking for, if you want to compute the ground state energy, then you need to find a special solution called the antiferromagnetic vacuum solution. So now comes an important step. So you need to define something called a counting function. So actually this is very simple. So you look at this beta ansatz equation, which is written as a product of this bunch of states, bunch of terms equals -1. So you look at the left-hand side, it depends on this uj. Now you just change this uj to some u, which is a parameter, and this defines you the so-called counting function. And for each solution of beta equations, you have one counting function. And since this z is on the exponent, we can take the logarithm. We can take the logarithm and then write it more explicitly like this. So And written in terms of counting functions, the Bethe-Ansatz equation takes a very simple form. So because the Bethe-Ansatz equation is this exponential equals to -1. So it means in the exponent, you basically have some integers or half integers like this. And this ij are called mode numbers. And the different choices of mode numbers correspond to different solutions of Bethe equations. And the antiferromagnetic vacuum is this state. Is the choice correspond to this choice of the mode number. So this is slightly technical, so I'm going to be rather fast. So the bottom line is, after you choose this mode, then you can manipulate your Bethe-Ansatz equations, which we see before, in a very smart way, so that you obtain this nonlinear integral equation. And this is a nonlinear integral equation for this counting function z. And you need to solve this equation numerically, then you can find the counting function, and then using this counting function, you can do a lot of things. So this equation looks like a TBA equation, which is familiar to some of the audience. And here this kernel is given in this explicit form. Okay, so
But
far,
you didn't take the thermodynamic
not yet.
over.
So even on the lattice, you can write like this. Okay, so suppose you solve for this Zn, then you just, after you find the Zn, you just plug in this formula, which will give you the energy, En. So this is still on the lattice. We did a lot of things on the lattice, and now we take the continuum limits. How do we do that? In the lattice model, we have the lattice spacing A, we have the size of your lattice, which is n, and now we have this theta. So theta has the physical meaning of some momentum cutoff. So in the continuum limit, what we are going to do, we need to take the lattice spacing to 0, and the size of the lattice to infinity, and also this rapidity momentum cutoff to infinity. And we need to take this limit in such a way that a times n is fixed, and this has the meaning of the volume of the field theory. So you put your field theory on the cylinder, and this r is the circumference of your cylinder. And also we need to keep this ratio fixed. So this has the interpretation of the mass of the particle. And after you take this limit, what you obtain is this guy. So you see where is the difference. Before you have this thing, which involves n, theta, and whatever. And after taking this, you obtain this. And so this is the Ningley, or the nonlinear integral equation for sine-Gordon theory. So how do you know it's a sine-Gordon theory? Because this kernel G, which we derived on the lattice, you find that amazingly is precisely the logarithmic derivative of the sine-Gordon theory, of the S matrix of the sine-Gordon theory. So that builds the connection between our Light-Cone lattice model, Light-Cone 6-vertex model, to the sine-Gordon theory. So you need to take this continuum limit. And in the field theory side, suppose you forget about all this lattice, what you need to do is to write down this equation where you take this S matrix and then compute this kernel, write down this equation, solve for Z, and then find the energy. So that's how you compute the finite size energy in sine-Gordon theory. Okay. And you can also compute other things like momentum. So now, again, TTbar deformation. So under the deformation, this S matrix of sine-Gordon theory is changed by multiplying the CDD factor. And this S matrix enters in this kernel. So how does this kernel get modified? So the kernel is a logarithmic derivative of this S matrix. And then you'll find that it will be deformed in such a way that you add another term. So this other term actually comes from the CDD factor. And then you plug this deformed kernel in your nonlinear integral equation, this guy, and you obtain this deformed equation. So this is actually in the original paper of Tateo and collaborators back in 2016. So you can massage this in a nicer way using some identities in trigonometric functions. You can massage this in a way that looks like the undeformed case, But here this r and this u this r is modified to r lambda, and then this u is shifted by some phi lambda. So in this way, people can solve the deformed deformed linearly, and find all kinds of properties of the deformed theory. So that's what has been done in Tateo's paper back in 2016. Okay, so now to our concrete question. Can we obtain the deformed linearly, which is this guy, by deforming the lattice model? What do we need to do on the lattice? So that's the new part. Now we're back to our lattice, and we look for this rapidity. So I told you this rapidity cutoff will play an important role. Previously, if we want to obtain the sign-Gordon theory, we just put theta minus theta, theta minus theta, right? Now suppose you make a different choice. Suppose now this theta n means this choice of spectral parameter at the site n. Suppose you make this change. You shift this theta universally by some sigma, universally by some phi, by some mu, and then you also shift this by some sigma lambda. Then you'll find that by going through the same calculation, you'll find that this driving term will be modified like this. And suppose we take the same continuum limit, we will find this deformed linearly. And from here, it's easy to see that you can make this identification. So suppose I choose my sigma lambda in this way, such that this combination will just be the r lambda, and I choose my mu lambda to be phi lambda, then I will obtain the linearly. So in terms of pictures, it looks like this. Previously, I have this lattice, and then I need to change this theta. So if I fix this, if I fix the mass, let me see, before I take the continuum limits. So if I fix my mass, and then I will find that deforming this theta is the same as deforming my lattice spacing. So it means that intuitively you need to do something with your lattice spacing. So this shift in this sigma, if you take mu equals to 0, because this mu will be related to the momentum of the state. If you take mu equals to 0, then this is uniform. You just squeeze your lattice like that. And then if you take this mu to be non-zero, then you also have some, this means you are deforming some non-zero momentum state. Then you need to further deform your lattice like this. So the conclusion is that if you deform your rapidity in this way, then you will obtain the deformed linearly in the continuum limit. So due to the lack of time, I cannot go into details to discuss more about this deformation, but this is the prescription. So I'm not completely happy about this prescription, and that's the reason I postponed a lot of time. I finally decided to put it out last year. And the reason is that, okay, there are some good parts about this prescription. The good thing is that integrability is preserved automatically, because at each point is still given by this R matrix, and the Yang-Baxter integrability is maintained. So I can make sure that the deformed lattice model is still integrable, and this is consistent with the fact that TTbar deformation preserves integrability. But there are also some very unpleasant features about this prescription, because I need to fine-tune this sigma lambda and mu lambda. So why? Because I need to tune my sigma lambda such that this combination is given by R lambda. And what is this R lambda? So this R lambda is related to the energy, to the deformed energy of your state. So it means that to deform each the rapidity locally, you need to know the global energy of your system. So this is a very unnatural fine-tuning. So it gives the correct answer, but I think this is not the most natural or the most beautiful way to do that. So that's so far is This is the unpleasant part. So in this direction also, we just started something. It worked to some extent, but there are a lot to be understood later. So let me conclude. We see that integrability is one of the motivations for TTbar deformation. And so we investigate two important aspects of integrability of TTbar deform theories. One is the form factor bootstrap, and we kind of generalize this thing. Actually, it's the other group which generalized this thing to the local operators, and then we apply. So let me. Okay, I will show them later. So we applied this to the branch point twist field and compute entanglement entropy. That we did at the same time. And also we investigate the deformation on the lattice such that in the continuum limit it gives you the TTbar deformed theory. So in the future, a lot has to be done. So first, in the form factor bootstrap program, we need to solve other models, like models with bound states, more type of particles, with non-diagonal scattering and so on. And then we also need to think about the connection to the CFT limit. And also for the lattice deformation, I want to search for a more local description. Because TTbar deformation, we know that it's like putting the theory on the random geometry. So can we somehow put the lattice model on some random lattice? Or couple this to some lattice gravity? So these are the things that we want to understand. And also we can try to combine these two methods and then compute some finite temperature one-point function. So, okay. And finally, let me show you the other group. This is important because they have the credits, these guys. Castro Alvarado, Negro, and Silas. Okay. So with this, I will end my talk. Thank you very much.
Questions?
So you said there might be a phase transition at some energy scale, and
I don't know. I just know something goes wrong.
okay.
I'm not sure if
And
phase
you
transition.
said that you can compute the entanglement entropy with TTbar deformation. So is it possible to detect the phase transition with this entanglement entropy?
Let me see. So it's a different thing. Entanglement entropy typically is associated to some states, usually the ground states. And then we compute entanglement entropy, and phase transition usually we consider some finite temperature partition function. So I'm not sure how can I
Usually they behave like very differently before and after the phase transition.
That's right.
Then you have to see the function as a function you choose lambda. Lambda is
Yeah, so I didn't show that explicitly, but it's some usual, it's some well-behaved function.
u.
Yeah, u is some constant.
Ah.
This is a Bechdel function.
But this is only for integral model, right?
This is for easing.
Okay. I mean the method.
Yeah, the method is only for
integral.
yeah, and even for integral models, I don't think this understanding is complete.
Any other questions? I have the same question as you. What's the meaning of what non-local? Why is it TTbar deformation non-local?
Yeah, as I just explained.
Yeah.
So either by looking at this asymptotic rows
Yeah,
of states, or by looking at this as matrix. Yeah, it's from this point of view.
You're mentioning something is exponential, but this is exponential in lambda parameter or some other parameter?
Exponential?
In what parameter?
In the Mandelstam arrow.
Okay.
Yeah.
So could it be that it's just some problem with parameterization? So instead of using lambda, one use log lambda, and then it's like a coordinate singularity.
No.
Okay.
I don't think
So
so.
it's a physical.
It's something more serious than this. Because you see this problem in the computation of many quantities. It's not just this. If you compute, say, two-point functions, you also find that this doesn't seem to be easy in the position space. You have to take the Fourier transform, and then you compute in Fourier space, and then transforming back, you will hit some problems.
In the case of the lattice deformation, in this last part, and if you change the sign of lambda, does that change your interpretation of how you perform the lattice?
If I
Change the sign of lambda, positive lambda, negative lambda.
this doesn't depend on the sign for the lattice deformation.
Any other questions? If not, let's thank the both.
Sorry, I have another question. So for lattice result, which part will you regard as universal for the description of lattice model?
Universal, so far what I think is that you need to do something with the lattice spacing. So this lattice spacing has to be tuned. So in some sense, it's like putting your theory on some dynamical lattice. And then you need to tune the lattice spacing in such a way that it depends on the energy of the state. So in the field theory, the correspondence is that there is a point of view on TTbar deformation which is doing a dynamical change of coordinate, going from one coordinate to another coordinate system. But the new coordinate system would depend on the stress energy tensor of the theory. And I think this is an analogy of that intuition. So I believe if you put your theory on some lattice using a different discretization method, then you also need to do something with your lattice spacing in order to obtain the non-local TTbar deformed field.
So eventually, do you think TTbar like deformation is well defined on lattice or not?
I think it's, so far my understanding is that it depends on the way you take the continuum limit. And I think there are some examples where so suppose one example is that before you can consider the Ising model on some lattice, and then if you put the Ising model on a random lattice, a completely random lattice, and in the continuum limit you will end up with coupling the Ising field theory to Liouville gravity. So this means that if you put some dynamics on your lattice system, there's a possibility in the continuum limit you'll obtain the field theory coupling to some gravity field. This is reasonable. But the gravity theory that corresponds to TTbar deformed theory, corresponds to TTbar deformation, is much simpler than Liouville gravity. So it should be some random geometry, but not that random. If you do completely random, you go to Liouville gravity. So I think we need to somehow have a good understanding about what kind of dynamics you need to put on your lattice in order to obtain